All right, so I'm going to go ahead and get started. I'm sure some more people will roll in, but they'll just miss some intro slides. So welcome, everybody. This is Steam Management's webinar series. We do this quarterly, and this presentation is going to be on industrial steam system assessments. We're going to talk about the process of executing industrial steam system assessments, and at the end, we'll do an example of a heat and mass balance. And kind of show you how I do that. There's a lot of ways to do that, obviously, but we'll go through how I do that. My name is Chase Bean. I'm the Director of Engineering for Steam Management. There is my email address. Some of you may have noticed we didn't have, or some of you that attended the first webinar, we didn't have the option on the registration to request a PDH certificate. So if you do want that, just email me. Sorry, I'm hearing something. Just email me at that email address there, and I'll make sure you get that for all you PEs and CEMs and other professionals out there. So the presentation learning topics today. So we're going to go over the industrial steam system assessment process, kind of just go over the common opportunities or efficiency scopes that we see, and then we'll talk about developing a heat and mass balance. And I'll go through an example where I kind of do a simple one, and we'll go through that. So to start off, so the steam system assessment process is split into 3 parts in the presentation. It's organizing the assessment, conducting the assessment, and then back-end development. So first, for organizing the assessment, first thing you want to know is what is the objective of the assessment? What is the client or your facility, if you're doing your own facility, what are you wanting out of the assessment? Obviously, this is often just cost savings, operational savings, and often in today's age, people are looking for a carbon footprint reduction. Those kind of go hand in hand. But then sometimes we'll get clients that are kind of maxed out on their steam system. So maybe they're actually just looking for capacity improvement. They want more available steam for their process. And that's another common thing we see. Sometimes they're looking for reliability improvement. They know that they have condensate building up in their distribution. They're getting water hammer issues. It's causing damage to equipment. So maybe they're wanting us to look at stuff like that. And then there's other targeted improvement areas. We get all kinds of different requests. Maybe they're having a problem with a particular piece of equipment or a particular portion of the system. But while they have us out, they want us to look at other efficiency scopes as well. And that's a common thing that happens. And then some clients are also interested in, converting to different equipment. Maybe they want to change their steam driven water heaters to gas fired, and they want us to look at the impact of that. Maybe they want to switch fuels on their boilers, or switch to electric boilers, something like that. So we look at those type of things too sometimes. Obviously, you want to come up with your schedule when they want to have the thing done. And then another big thing that people kind of overlook is the system access. So just because you have a contact and he's allowed you on site, you need to work with him and make sure that all of the different area managers know that you're going to be on site, what you're going to be doing, that they're going to let you access the equipment that you want to look at, and find out what's going to be in operation. Because if the system or that portion of the system's not on, you're not going to be able to evaluate it very well. And make sure you have the proper site escorts coordinated if that's required on the site. And then what are your safety requirements? So what is the training required, and what is the PPE required? Every site is not, standard PPE is boots, hard hat, glasses, hearing protection. But there's other things different sites will require, like gloves or long sleeves. Sometimes you need special boots like metatarsal protection. Sometimes you need double hearing protection, non-static clothes. Maybe it's even a hazardous site and you need LEL monitors for somebody said, is it normal? No sound. Should be sound. Is everybody hearing me? I don't know if
You got a thumbs up by someone, a couple of thumbs up coming through. I can hear you.
okay. All right, great. All right, sorry. Lost whoever asked that, but yeah, you should be hearing. So apologize if it's not working for you, but yeah. Anyway, yeah, so proper PPE is important. There's other limitations I mentioned. It could be hazardous conditions on the site. Like you'll hear Class 1 Div 2. That means that gas or explosive gases may be present in the site. Class 1 Div 1 is gases are definitely present in the site at all times. Some facilities, like manufacturing facilities at pulp and paper plants, for instance, they might have radioactive materials. In certain locations, chemical plants have all sorts of dangerous chemicals that they'll train you on how to avoid or what to stay away from. And so in industrial facilities, there's all sorts of hazardous conditions that you need to be aware of. And then I like to point out photography. Like you have to see if you can get if you're allowed to take photos on the site. That's a big thing with our data collection, and a lot of sites have limitations there. And sometimes you don't really find that out until it's too late. But picture is blurry on the slides. That's okay. This picture is not really showing much, but oh, the whole picture probably. I hope that's not true for everybody. Anyway, yeah, if you can't take photos on the site, that's very limiting, and it'll actually, you need to account for the time required to write everything down when you're on site. So that's another big thing. Initial data gathering, this is just getting all the drawings and documents that you need before your site visit. You want to get as much data as possible. It's very frequent that you don't get everything that you asked for, but some big things here like utility bills. Utility bills obviously give us the costs for fuel and water, but they can also give us other information, like if we know what utility you're using, we can research rebates. We can look up fuel quality and water quality and those type of things. And those are all involved in savings calc. So that's a big thing. For me, system PNIDs are great to understand the system ahead of time. It's also a great thing to take notes on when you're walking down the system. And so those are great to have. Everybody doesn't have updated PNIDs, so just kind of another wish list item. But another big thing is a system layout. Again, it's that's a great thing to have for note taking and just to get the lay of the land before you get to the site. Another big thing for STEAM systems is trap survey reports. So one of the biggest opportunities in STEAM systems is trap maintenance. And so at some point, most systems have had some sort of trap survey done, and it's great to get that report ahead of time so we know what the trap population looks like and what we're getting into there, particularly if we're coming on to do a detailed trap survey. Steam loads, how are they operating the system? Any boiler and other equipment performance data, or just model numbers, and we can look that type of stuff up. So it's great to know as much as you can about all the equipment involved. If they have a fuel analysis or higher heating value of the fuel, and water quality analysis. So on to conducting the assessment. So first off, when you get to the site, you're usually going to do your safety training. If you haven't already done it, some sites nowadays will do it. You'll do it online before you get there or something. But oftentimes you're going to sit in a room and watch a video and take a quiz. It's real important to pay attention to these. It's that every site's different. Every site has different hazards. different rules, different alarms that you need to listen out for, different evacuation points. So yeah, this is a important step. Then you'll have a kickoff meeting. So you'll sit down with your site contact, other stakeholders in the system, and just discuss what your intentions are. Hopefully, you've done a lot of this up front. A lot of times, people just can't make time, and once you get face to face is when you're really giving them a lot of clarity on what's going on. But hopefully, you've done it beforehand. But you'll kind of talk through the scope, where you're going to go, where you're going to be. They'll tell you safety concerns, who you need to talk to, who you need to be escorted by, um, you know, all kinds of stuff. And then you'll go out and do an initial walkthrough. So this is kind of like your visitor's tour of the facility. Maybe you take some photos, maybe you gather some data, but it's not your detailed data walk down. This is just like a lay of the land walkthrough. Then you'll come back and you will, excuse me. You'll come back and sit down and hopefully they are able to get some guys to make time for you, like the different specialists at the plant and the area managers and other people operating the steam system. And you'll talk to them and ask for info, trend data, drawings that you weren't able to get, problems that they see with the system, and kind of start developing more of a feel for the system and what you want to look at. And then you'll move on to a detailed walk down. And this is, I say detailed walk down, but this is like the rest of the assessment, right? Is like all data collection, just poking around the system, not actually not messing with anything. If it's, you don't want to touch a lot of stuff or be flipping valves or anything, but crawling around and seeing the whole system and really gathering as much data as you can. Some of the things, big things you want to get are like nameplate data, pictures of nameplates, pictures of control screens. If you don't end up getting any trend data from their control system, control screens is a great place to see, how the equipment's operating. Nominal sizes and dimensions of piping and equipment, and maybe even you're already thinking about new equipment that you want to put in, and you're measuring space available for that, or piping runs that might be required. Temperature measurements, thermal images, gauge readings. I love to take like a P&ID, like I said, and as you're making sense of the system and you're walking down the piping and you're identifying gauges, I like to write down what they read on the P&ID. So really, you're just getting all the data you can. And then between walkdowns, you'll come back to wherever your designated meeting room is. And, if you got your other guys there with you or your site contact, and you start talking through things. I saw this, I saw that. What else do we want to go get? What's missing? And start thinking about, how you're going to calculate savings and how you're going to verify the savings if you are to implement these measures. And then at the end of that, basically the assessment is a lot of data gathering. You always kind of feel like you're going to miss something. I find that I generally use the whole time that we've allotted and just keep walking things down and seeing what I can find. But at the end, you do a closing meeting. You talk about what was found, talk about the opportunities that you think are available, and maybe what's involved. What are the scopes of those opportunities? Back-end development. So a big thing for steam systems is developing that heat and mass balance. We'll go through this in some more detail a little later. You want to qualify all the opportunities that were found. So basically, this is where you're determining the savings, evaluating any other benefits that there might be from implementing those opportunities. What is the effect on the other equipment? And what's the feasibility of the project, and what do you think the cost of the project will be? And we work out project estimates for those. All that is bundled up in the assessment report. This is like a very organized report where we just go through. We actually will number each of these ecos, or they're also called ECMs, energy conservation measures. And we'll number those, and for each one, you give a description of the opportunity, estimated savings, scope of the project, and then hopefully, if you have enough information, an estimated budget. And we usually can give a budget of each one. Maybe we vary how budgetary each project estimate is, just to give them an idea of how much more we need to tighten that up to actually implement it. And that's so once you send that assessment report out, that's kind of the end of the assessment. But I wanted to talk about some of the efficiency scopes that we see. We're going to split these into generation, distribution, end use, and recovery. You may remember this slide from our last quarterly webinar, but we're not going to get into as much detail on these as we did then. We just kind of want to give a high level overview. Generation is your equipment in your boiler house or opportunities in your boiler house. Distribution is your steam distribution piping. End use are your your steam users and your steam consumers. And then recovery is your condensate piping and collection tanks and pumps. So I kind of listed these out of order, but it's actually in order of the things that are most common. So distribution opportunities are the most common things, and the most common of those being steam trap maintenance and monitoring. That's your kind of your big energy waster in a steam system if it's not properly maintained, and so that's often the biggest opportunity. Then thermal insulation is another big one. Uninsulated steam components are a big waster of energy, and as the heat is lost, that generates more condensate in the system, which can lead to more water hammer and cause reliability issues or premature failures on equipment as well. Steam distribution automation is another one. Pressure reduction, identifying leaks, and then there's some others listed there. Excuse me. Recovery opportunities. The most common is to just improve the condensate collection and return equipment. Make sure the pumps are working right. Maybe we look at the configuration, redesign it. You want to make sure you're getting all that condensate back to your boiler plant. Condensate obviously has a heating component that offsets some fuel usage, but if you think about it, it's also treated boiler water that you don't have to pay for the makeup water if you can get your condensate back, and B, you don't have to pay to treat that makeup water. So it's a big cost saver to be able to return the condensate. Generation opportunities. These are opportunities in the boiler house. So the most common of these that we've been seeing lately are blowdown heat recovery and blowdown control upgrades. We've been seeing a lot of combustion optimization like O2 trim systems and things like that. And then economizers or combustion air preheaters are good opportunities as well. There's some others, I won't read all those, but yeah, a lot of opportunities in the boiler house as well that you can evaluate. End use opportunities. These are less common for us to evaluate because this is really replacing the actual steam users. And in an industrial facility, I mean, we can help evaluate if they're performing as intended or how we can improve the steam going to those pieces of equipment. But most times, this is a big piece of equipment that the facility is going to decide themselves if they're going to keep or not. These are big log vats here, so these are a bunch of control valves going to big steam vats. All right, so now we'll get into Well, I guess I should stop there. Have there been any questions, Megan? Or does anybody have any questions? I think you can, I
haven't seen any come up yet, Chase.
okay, if you do have any questions, I know you can't unmute yourself, but you can type them in the chat or in the Q&A section on top. So just let me know, and we'll stop at any point. But okay, so we'll get into developing a heat and mass balance. So this is kind of the bulk of the presentation, and we're going to get a little technical here, but bear with me. Hopefully you find it as interesting as I do. So the basis for the heat and mass balance is basically the first law of thermodynamics, right? So energy is neither created nor destroyed. Any energy into the system has to equal the energy out of a system. And then you also have a conservation of mass law. So mass into the system equals mass out of the system. And then for each flow point, we're going to need the mass flow and then the heat content. Luckily for steam systems, the heat content at each flow point you can get from steam tables, even on the water side. So, and I'll show you that in a minute. But and then we need to know if a phase change occurs, what's the impact there? But that's also kind of a heat and mass balance in itself. So this is the system that we're going to look at. We have this is a deaerator. It's feeding feed water into a boiler. The boiler's generating steam. Some of that steam is going, or most of that steam is going out to the plant. Some of it is being used in the deaerator. So all of the, if you're saying you have 100,000 pounds per hour of steam to the plant, the demand there, you're having to make more than that to, feed your deaerator. So we're going to evaluate the impact of a blowdown heat recovery skid. So this is basically a flash vessel where the surface blowdown from the boiler, and I guess I should explain what surface blowdown is, but surface blowdown is a continuous stream of water that's taken out of the boiler right at the surface to remove impurities from the boiler water. So this is a necessary waste heat stream because you're having to take water that's heated all the way up to saturation at the boiler pressure and then just reject it from the boiler. So this is typical for like 2 to 5% of the boiler capacity to be lost through blowdown. And so, recovering some of that heat and that flash steam from that is a great opportunity. So that's kind of what this system is. So this flash tank and this heat exchanger, that's a blowdown heat recovery skid. So you have surface blowdown going in. It will flash off to steam, and you can use that steam in the deaerator. Even though this is dirty boiler water, the flash steam flashes off clean. So that can be used. And then the drain will go through this heat exchanger here and basically preheat makeup water going to the DA. So all of your water lines are in blue, blowdown lines are in turquoise, and steam is in pink and orange here. So that's the system. So we're going to look at this system. But first, I kind of want to give you like an idea of how we're looking at this. So the whole heat and mass balance is basically a heat and mass balance of all the components, and then they're all kind of tied together. So this is the concept of a heat and mass balance for just the deaerator, right? So your energy out is going to be equal to the mass flow of P1 times the enthalpy of P1 plus your vent steam, mass flow of that times enthalpy of that. So those are your energies going out of the system, and then your energies going into the system are your steam, your total steam P7, condensate return P19, and your makeup water P18. So if you set those equal to each other, that should be the same amount of BTUs per hour on both sides. Alternatively, you can put them on the same side, right? And then all of those energy flows together should equal 0, which is how we do it in the table.
Hey, Chase, If you don't mind me interrupting, we have a question from Clade.
Okay.
The question is for pressure reduction. For pressure reduction, is there a typical rule of thumb for distribution losses? For example, if there is a hospital making 100 psig steam and the highest user is steam sterilizers at 60 psig, is there a way to estimate what the psig should be at the plant for the normal conditions? No blowdown through traps, leaks, etc.
I don't know if let me think about that. I don't know if I completely understand the question, to be honest. You have a 100-pound steam and you're going to 60-pound steam, and you want to know. I don't know if I understand what he's asking there.
Maybe I can open it up to Clade so he can. Let me find your Clade. Allow mic. Okay, Clade, you should be able to talk now.
Yeah, sorry. So we look at hospitals a lot, and they have CUPs, central utility plants, and one of the main things, they usually make 110, 100 psi steam, but they're a typical hospital load anyway. The highest steam users usually their sterilizers at 60, so there's always a steam reduction opportunity, but we kind of just say, bump it down a little bit, see if anything goes crazy. If it doesn't, bump it down a little more. Is there I'm just asking if there's a rule of thumb. So if you had 100 psi steam, then the end use would be X. If it's 90 at the plant, then the end use would be Y. Something like that.
No, I don't think so. Yeah, I don't know of a rule of thumb as far as how high you want the generation pressure compared to the end use pressure.
Okay.
I think that's just something I would evaluate on a case-by-case basis.
Cool, thanks.
Because in steam set you have all sorts of generation pressures, and then I worked on a power plant where you had 1430 psi steam, and there were all different levels of system pressures that came off of that, down to 10 pounds of steam. So yeah, I don't know that there's a set rule of thumb there, but
Travis Mosher had chimed in on the chat saying the pressure should be set according to how the boiler is designed.
yeah, I agree with that. And then you're going to spec your boiler for what you need, and what the distribution piping is designed for. If your pressure goes up, your diameter of your piping can go down for the same mass flow, and so it's really just a whole design effort. But yeah, if you do go into reducing system pressures, you got to keep an eye on your velocity of in your steam piping, because as your pressure goes down, your velocity goes up for the same mass flow, and you can get your steam screaming through those pipes too fast if you're not careful. Anyway, good question. Yeah, so back to this. So we did the aerator heat and mass balance. This is a any kind of flash tank mass balance, basically. So your pressurized condensate in, when it gets to the lower pressure in the flash tank, some of it's going to flash off. And the way you can determine your flash steam percentage is that the heat and mass balances out. So your inlet is going to equal your outlet and your drain outlet. And then there's another equation should be in here, but also your mass of P11 equals your mass of P12 plus P13. So you have two equations there you can solve and get your flash steam percentage, basically. So I'm going to stop now and actually go through the example. Hopefully that made sense, kind of the concept of what we're doing here. Again, this is just a calculation. So there's a lot of ways to do this. This is just how I generally do it. There's a lot of different tools you can use to do this. There's tools on Department of Energy website. You don't have to do it from scratch like this, but I will take our heat and mass balance and run all sorts of other calculations off of it. And so I just really like to do it in Excel so that I can do whatever I want. And that's my preference. So By all means, if you want to do it a different way, that's fine. But hopefully you can find something useful out of this. So this is basically our simple design basis for the project. We have natural gas as the fuel cost, hydroheating value of the fuel, water plus sewer cost, just some round numbers here for simplicity. Steam demand to the plant of 100,000 pounds per hour, operating all year, 200 pounds of steam, 40% condensate return. So that's steam flow to the plant. That's based on steam flow to the plant. Condensate return temperature, makeup temperature. We have a sewer limit here. So you can see the drawing again is over here. The water coming out of the blowdown tank in the drain has to be under 140 degrees. So that's what that means. It's just material limits of the drain system, and 140 degrees is a common limit there. Some plants don't have that limit. I was at a chemical plant recently, and they did not have a sewer temperature limit. They just had a higher rated materials in their drain system, and so it eliminated that component of the savings. But there's tempering water that's required for that, and so for these blowdown heat recovery opportunities, that's a big part of the savings. The boiler fuel efficiency is 84%. The blowdown percentage of the boiler is 5%. Deaerator pressure 10 pounds. Deaerator vent rate is 1%. And the blowdown heat recovery manufacturer has given us an expected performance of 90-degree outlet. So there's a lot of numbers there, but these are kind of they're intended to represent like the type of things that you would gather on site, the type of data points that you would gather, and then come back to the office and start building out a heat and mass balance. So these first 6 or so fields are templates. So I will copy these out kind of as a block for steam flows, condensate flows, feed water, etc. So for each flow point here, I started doing this already just to kind of so we could get through setting up the whole thing. But so at P1, it's a feed water, so I'm going to copy feed water, etc. So I've gotten down to P10, which you can see is right here. So P11 is also similar flow. P13, not P12. P12 is flash steam. P13, P14. Let me back up a second. So I wanted to point out, like, on each of these blocks, the blue fields are inputs, and the other fields are calculated. So the saturation temperature here on this line, this is looking up based on saturation pressure. The enthalpy is looking up based on the saturation temperature. Density is looking at, so I have formulas in here. It's actually a macro that I have that's looking up steam properties. So as I adjust pressures and temperatures, those formulas will update the properties. You can do this just by manually looking up these properties. I would highly recommend having some sort of automated property lookup. But you can do that however you want. It doesn't have to be a macro. It could just be an Excel version of steam tables or whatever, and you have lookups going on. But you definitely want to get this set up first. Anyway, so we'll continue filling this out, and I won't fill it out all the way. But then as you, I'll hide these templates here. Once you get it filled out, you start coming up with relationships, right? So you say, well, P2 is going to be equal to P1. So I'm going to set that equal to that. And then I'm going to, I like to have blue as an input, right? So once something is an equation instead of an input, I'm going to unhighlight it. Let's say P3 or P4, right, is steam to the plant. P3 is going to be equal to P4 plus P5. And you just start doing these relationships down through the whole table. And I know what you're thinking. I'm not going to make you watch me do this whole thing. I kind of did like a cooking show kind of style here, where I have my final product on the next tab. So here it is. It's all developed. We have the templates hidden, and then all of the flow points are built out. Our condensate return here is 40%. That's calculated here. DA vent rate, 1%. And everything is calculated with blue fields as hard inputs. These green fields are the balance fields. So in the end, I have every relationship in the system accounted for, but then there's a loose end at the deaerator steam flow and the tempering water flow. And so those have to be balanced out. So you see this balance is kind of like what we showed in the slides. I have all of my flows to the deaerator and from the deaerator set here. It doesn't show a mass times the heat balance because that's actually just calculated here. So for each flow point, I have a heat carried component. Anyway, so if I was to change the steam going to the plant, say to 120,000, you see that this is no longer balanced. So I'm going to goal seek this to 0 by changing, I highlighted this field green so you could see what the balance points are. And that changes your steam flow. Now our tempering water balance is off a little bit. So I'm going to goal seek that by changing this flow. And now everything's balanced again. Okay. So that's the idea.
Chase.
Yes.
Chase,
Sure.
I'm going to interrupt you just real quick. We had a question from Ferris. Is this spreadsheet a handout for the webinar?
No, it is not. It's got some proprietary macros and things, but I could maybe do like a PDF of it or something so you could kind of get the layout. And then you can, like I said, you could develop your own lookup tables or whatever for your steam properties. As long as you understand the concept, you can certainly set it up. Also, all the relationships here, I don't, like if I was to get another boiler plant, I wouldn't just copy this heat and mass balance and then paste it over. I would start over from scratch with those template fields and just build it out again, because there's too many relationships and there's too much opportunity for error. It's kind of better to just build it from scratch. So as far as setting up your own, the hardest part would be just doing the property lookups. Anyway, so this one is set up. So this tab is set up so kind of to the effect that this blowdown heat recovery tank does not exist. So if you look at P8, a little too far, and then going to P10, it's just the same. None of the flash steam has come off. Pressure is the same, like temperature is the same. So the intent here, and the same thing on the other side, right? Like so P17 to P18, the water temperature is the same. There's no impact. So we're calculating our annual fuel cost based on no blowdown heat recovery skid. Then there's also a water cost here. So this is your makeup water plus your tempering water. So again, when we don't have to have as much tempering water, this is going to go down as well. The annual fuel cost here, this is something that people will do, and they'll just take like the energy of the steam out in the plant and divide it by the boiler efficiency. Well, that's not accurate. So this is wrong here, but I put it here just to show the difference. So this is your fuel cost based on your actual boiler. Where is that? Oh, sorry. The boiler firing rate is here. So this is your actual boiler steam outlet. which is much higher than just your steam to the plant, right? You got another 16,670 pounds per hour steam. So your annual fuel cost is much higher than if you just take your steam flow to the plant. And that's another thing that the heat and mass balance helps figure out. And that'll change based on condensate return, temperature, your vent rate of your steam, of your deaerator rather. So there's a lot of components here, and you're starting to see why it's necessary to do this whole balance. Anyway, so we'll go on to the next tab where we have actually calculated out. Go ahead, Megan.
Chase, can I, another question came across. Water cost is for the makeup water, which is 60% condensate? Question mark.
Water cost is for, yes, so the makeup water is 60%, 60% makeup, which is pretty high. Not uncommon though. 60% makeup water and the tempering water. So if you look at the tempering water P16, there's a 7 GPM component there of tempering water. So you have 133 GPM makeup water, that's about 67,000 pounds per hour. You're talking about a boiler outlet of 116,000 pounds per hour. Yeah, so it's probably higher because we're saying we only get 40% of the steam to the plant back. So that's even less of a percentage if you're talking about total boiler outlet flow. Yeah, good question. Thank you. Okay, so we'll move on to the next tab where we have a blowdown heat recovery skid and the impact of that. And so basically, there is no more tempering water. The manufacturer has said that at the operating loads that we've given them, they're expecting the drain or the P11 flow here to be about 90 degrees. So it's going to go from 239 degrees to 90 degrees, and that's going to heat our makeup water up from 50 degrees to 60.8 degrees. Now this temperature is now one of the balance points for the whole balance. And you see there's no tempering water. So if you're, yep.
The follow-up question, tempering is blowdown?
Tempering water is your blowdown coming out of your blowdown tank is coming out at atmospheric conditions. So before you have the blowdown heat recovery skid, it's going to come out around 212 degrees. And so we have this sewer limit of 140 degrees. And so on the other case, you have a required flow rate of water to temper that temperature down. So your P13 temperature is going to be 212 degrees. Your P16 temperature is 50 degrees, and you're adding a certain amount of water to get this P14 temperature down to 140 degrees. So that's what that is. So once this blowdown heat recovery skid is installed and your P11 temperature is now 90 degrees, you have no more flash steam, which that was going to atmosphere and being lost anyway, and we're not conserving that. All this is going to drain, but you have no more flash steam, and you have a drain here on your blowdown tank that does not need to be tempered anymore. So that's part of the savings here. So if we go back to this tab, this is being balanced. The deaerator balance is still there. You have less deaerator steam. You remember the number on the other tab was 16,000. That is due to now you have your flash tank here and you're capturing some of this flash steam. So you have this component here. You're also, that's not making up for the 14,000 or the old 16,000 number, but the reason that the total is lower is because you are now preheating this P17 flow with your blowdown heat recovery skid. And so the makeup water is now going to be 60.8 degrees instead of 50 degrees. And so that reduces the amount of steam that you need in your deaerator. I know this is maybe hard to take in. You're looking at a lot of numbers and me flipping things around. But hopefully you're kind of getting the idea of it. It's an in-depth calculation. It's a big math puzzle. If you like math, you'll like doing this. But basically, we use this to calculate all the streams, and here you can see your new fuel cost. You're still in the 11 millions, but you're saving $258 or $259,000. And then you're saving $211,000 of water just from your tempering water not being required. And so your total savings here is $470,000 for this blowdown heat recovery unit for a $12 million fuel cost, or original fuel cost. Well, it's not just fuel cost, it's your total cost. Again, this is down here. This is just, I'll delete this, but this is like the wrong way to do it. So that's it. That's kind of it in a nutshell. This takes hours to do, so we could spend hours looking at it if you wanted to be bored to tears. But I'm going to share the presentation again. We'll get to the end. So now it's just I'm just getting to the questions slide, and yeah, that's the end of the question. And I have left some time, or at the end of the presentation, rather, I've left some time for questions.
Chase, the first one from Jamie, what is the MPV or IRR for a typical BDHR type of system?
That varies plant by plant. It's usually a pretty good payback. It depends on your fuel cost. It depends on your water cost. It depends on your blowdown percentage. Depends on your deaerator pressure. Yeah, it varies. It's not uncommon to get one that pays back within a couple of years, which is a really good payback. For most facilities, it's going to meet their internal payback requirements for project approval. Yeah, it's a great opportunity if the conditions are right. I see another question there. Does this heat and mass balance consider radiation losses from each facility? How is the amount of radiation losses generally calculated? It does not consider that. That's a whole nother level of complexity, but you certainly can add that in. Like boiler radiation losses are usually just given in a percentage, like a 1% radiation loss. You could add in what you think based on your insulation that is in the plant. You could add in, okay, this section of piping is 500 feet long. We're losing this much per foot. So let me just throw in, okay, by the time you get from this point to this point, you've also lost this many BTUs, through your pipe wall and your insulation. So you can add those components in. And again, that's why I love to do this in Excel. I can add in whatever I want to the system and account for whatever I want and ignore things that maybe I think are negligible or whatever. But it's not too common to add in like thermal losses in piping, at least in industrial facilities, because it's usually pretty efficient. I mean, there's like a lot of insulation missing sometimes, but their systems are usually higher pressure, and the amount of like thermal losses is more negligible compared to the actual energy being used. Although, like I said, there's still a lot of savings there if there are uninsulated components. Anyway, yeah, thanks for that. Is there a tool on your website to estimate savings to steam plants? No, we don't have like a downloadable tool. Maybe that's a good idea though. Maybe we should generate something like that. I would recommend on the Department of Energy site, they have some good tools. If you're doing like kind of generic calculations, again, like I don't ever use them because I want to be able to go in and fine tune things. But yeah, there's some great resources out there for that on, especially on the Department of Energy side. I would recommend, especially if you're not a steam system expert, it's kind of intuitive enough that you can get some good numbers out of it. See another question. In a hybrid steam system, natural gas plus biomass or natural gas boilers works as a backup for demand. Do you expect bigger efficiency losses in the natural gas boiler, even though advanced flow regulators are used? Advanced flow regulators, are you talking about the gas flow to the boiler or air feeding? Okay. Do you expect bigger efficiency just in the boiler itself? Yeah, I would say that a big biomass boiler is generally going to be less efficient than a gas boiler. Biomass, people that are using biomass, at least in industrial facilities, especially like pulp and paper manufacturers and maybe like sugarcane plantation or something like that, they're often using it for the reason that it is inexpensive to them. And so even if it's less efficient, it may be their more cost-effective fuel. Yeah, sometimes the payback is not there on biomass facilities where it might be there on natural gas. It's all just depending on what the fuel cost is and those things. But yeah, we would take the expected operating cases at each boiler, and we can compare those on different operating cases. Once I get this set up on the heat and mass balance, honestly, I will usually write a macro to do all the balances. So all I have to do is click a button. And then I'll run a bunch of I can just run whatever cases I want, whatever makes sense to me, kind of just to see if anything stands out. And then I'll publish like the most interesting cases to the client. And maybe like you have a minimum flow case, a high flow case, an average flow case, or maybe you have an all natural gas flow case or an all biomass flow case. And I have like combustion analysis tools that I can do too, and do an airside heat and mass balance where you go through all of your airside components for the boiler. Not very interesting on a natural gas boiler, but when you get into a biomass boiler where you have maybe a combustion air preheater and an economizer and some other components, you start adding in that airside balance, and there's other things to evaluate there. But yeah, I don't know if that answered your question, but hopefully a little bit. What is the estimated savings from installing a heat recovery on blowdown to preheat makeup water and the payback roughly? Well, this is a fairly realistic example for an industrial facility. This is a high steam flow. A lot of facilities are going to be maybe closer down to 20 or 30,000 pounds an hour or something like that if it's just a small manufacturer. This is a hefty size steam flow. And this is a realistic saving. That's a realistic gas cost and a realistic water cost. I would say a couple of years, 2 or 3 years with these conditions. Yeah, great questions. Thank you, everybody. Is it any other questions? I wanted to, while we're waiting on other questions before everybody jumps off, I wanted to point out, so we're doing this webinar the last Thursday of every quarter. So we'll send out an invite for the next webinar, but it will be on June 29th as of now. We'll let you know if that date needs to change, but as of now, it'll be June 29th. I also wanted to point out I was on a podcast it's called Better Building System Podcast, and they had me on as a steam expert, and we talked about kind of the future of steam, and the episode is called Steam, Anybody Making It Anymore? You bet. That's the title of the podcast. So if you're interested, I think it came out pretty good. Go check that out. And also, I wanted to say again, the PDH certificates, if you want one, just email me at that email address there on the screen, cbean@steamngt.com, and I'll make sure to get that over to you. Yeah, that's it. But I'll hang on for a little bit if there's any more questions. Thank you, everybody, for attending. I hope you got something out of it, and we will see you on the next webinar.
It just came out.